Hello and welcome to this video on orthogonal complements. Alright, so in this video I'm going to first, like most videos, discuss the definition of what does it mean, what do I mean by orthogonal complement to some subspace of an inner product space, and some important results involving orthogonal complements will be stated. Not necessarily with proof, that's not the point of this video. Maybe I'll put out a video at some future date where I go through and write out proofs for all these results for you. But for right now, I'm just going to state the results that are pretty important regarding orthogonal complements, and then I'll go into some examples where I have to determine whether or not two given subspaces of an inner product space are orthogonal complements. And then my final examples in the video, I'm going to be given a subspace of some inner product space and asked to find its orthogonal complement. Okay. So on the first page, I have what does it mean? What is an orthogonal complement? So if W is a subspace of an inner product space V, and that's some vector space with a properly defined inner product. In my examples today, it'll be the dot product on some Euclidean space. Just know that you might come across examples out there involving non-Euclidean spaces and other inner products, but today the examples will involve only Euclidean spaces and the dot product on those spaces. Alright, so starting over, if W is a subspace of an inner product space V, then the orthogonal complement of W, denoted W, orthogonal complement, or W with the orthogonal symbol as like a superscript. This is the orthogonal complement of W, is the set of all vectors in V, right, all vectors in the vector space V, that are orthogonal to every vector in W. Alright, so a way to write that symbolically would be the orthogonal complement of W is, all the vectors in V such that their inner product with any vector in W is 0. Right, that's what it meant for vectors to be orthogonal, right? Their inner product was 0. So it's all the vectors V in V such that the inner product of V with W equals 0 for every W in W, for any vector in the subspace W. All right. So some important results here. One thing is that if W is a subspace of V, this orthogonal complement of W will also be a subspace of V, and I've written that out here. The orthogonal complement of W is also a subspace of V, so it itself is a vector space. It's non-empty, right? 0 would belong to the orthogonal complement of W, since the inner product of 0 with any vector from W would be 0, right? So it's non-empty. Closed under addition, if you took two vectors in this orthogonal complement and added them together, you could show that using some properties of the inner product, the additive property of an inner product, that their sum would also be in the orthogonal complement. So it's closed under addition, and it's also closed under scalar multiplication. Right? If you could use the homogeneity property of inner products to show that if a vector belongs to this orthogonal complement and you multiplied that vector by any scalar, the scalar multiple will also be in the orthogonal complement of W. Right? And so the orthogonal complement of a subspace is also a subspace of the vector space V. Okay. Another important result. In one of my more recent videos, I talked about what is the sum of two subspaces of a vector space. Well, our vector space V is going to be the sum. And again, I'm not going to have a proof for this just yet, and I'm also going to, in a future video, show you how this expression can be done. But the vector space V is equal to, it's a subspace of V called W plus its orthogonal complement. All right. So V would be equal to W plus W, the orthogonal complement of W. When I say this, this means that every vector in V can be expressed as a sum of a vector in W and a vector in the orthogonal complement of W. All right, so I could take any vector in V and write it as a sum of a vector in W plus a vector in its orthogonal complement. And how we're going to do this, I'm going to do in a video later, or another video on orthogonal projections onto vector spaces. But for right now, just know that this can happen. So the vector space V is the sum of a subspace and its orthogonal complement. Also, because they're orthogonal, right, these would be orthogonal subspaces. If you recall from, again, I hope you've been watching, hopefully you've been following. I had a video up recently previous to this on orthogonal subspaces. And if you recall, that orthogonal subspaces have an intersection that's the zero vector only, right? The only vector they would share in common is the zero vector. Right, so the only vector a subspace and its orthogonal complement have in common is the zero vector. And then putting these two things together, these two results, the fact that our vector space, our larger vector space, is the sum of a subspace and its orthogonal complement, and that any subspace with its orthogonal complement have an intersection that's only the zero vector, then we could say that the vector space is, putting those two together, is the direct sum. Remember this little plus sign with a circle around it. Again, I hope you've been watching my previous videos. I had a video on sums and direct sums before this. Then our vector space V, the larger vector space, is said to be a direct sum of a subspace and its orthogonal complement. And when I'm saying this, what this means is that not only can every vector in V be expressed as a sum of a vector in W and a vector in the orthogonal complement of W, not only that, but it can be expressed uniquely as a sum of a vector in W and a vector in the orthogonal complement of W. Right. So that means if I took any vector in V, I should be able to write it as a vector in W plus another vector, a vector in the orthogonal complement of W, and I should only be able to do this in one way. Right. It should be I'll be able to express a vector from V uniquely as a sum of a vector in W and a vector in the orthogonal complement of W. Again, I'm just writing these out right now, without proof. All right, but just know that these are important results with regards to orthogonal complements of subspaces. And exactly how to do this, as I mentioned earlier, how do I take a vector in a vector space and write it as the sum of a vector in a subspace plus a vector in its orthogonal complement? Like I said, I'll be showing you how to do that in a video after this. I just want to get these results out here, and these will come back in that video as well. All right, so my next part of this video is just going to be some examples where I'm looking at a couple subspaces of a larger inner product space, and just asked, are these subspaces orthogonal complements? Right. So for the next few examples, my instructions are the following. Determine whether subspaces W1 and W2 of inner product space V, determine whether these two are orthogonal complements. So my first example here is in R2, and all my examples in this video are from R2 or R3, but just know that you could go to higher dimensions, R4, R5, R6, whatever, or non-Euclidean spaces. But just pay attention to what the inner product is, and in this video it'll be the dot product, the inner product. Because remember, the concept of orthogonality depends on how the inner product is defined. Alright, so here W1 is the span of the set with the vector 3, 2, right? So it's just all scalar multiples of the vector 3, 2, which is going to form a line right through the origin in R2. And W2 is the span of the vector, the set with the vector negative 4, 6. Alright, so this is the all scalar multiples of the vector negative 4, 6. So again, another line in R2. And as I mentioned, these are subspaces of R2. Right? All these are collections of vectors with two components. So these are subspaces of R2, and the inner product will be the dot product that I'll be using on R2. Right. Now, the question is, are W1 and W2 orthogonal complements? All right. So to answer that question, are these two, orthogonal complements? I really need to be answering 3 different questions. All right. The first of these, one, is are W1 and W2 orthogonal subspaces? Are W1 and W2 orthogonal subspaces? And again, I had a video about this previously where I showed you how to determine if two subspaces of a vector space were or of an inner product space were orthogonal. So this is the first question I would ask myself. Now remember, you could just say, remember that in order for two subspaces to be orthogonal, every vector in one space has to be orthogonal to every vector in the other space. So you could set it up where you take a general vector from W1, right, some scalar multiple of 3, 2, and do the inner product of some general vector from W2, right, some scalar multiple of negative 4, 6, and show that the inner product will always be 0. Right? When I take a vector from W1 with a vector from W2, their inner product will always be 0. Well, instead of doing that, remember, you can just look at the basis vectors. Right? Obviously, the way I have these written, it should be obvious what the bases are. The set with 3, 2, right, is a basis for W1, and the set with negative 4, 6 is a basis for W2. So my basis vectors here from W1 is the vector 3, 2. From W2 is the vector negative 4, 6. So there's only one pair of vectors I really need to check here. All right, I just need to do the inner product of a basis vector from W1, which is the only one is 3, 2, with a basis vector from W2, which is just negative 4, 6. Right, so very simple. Just that one inner product I need to check. And this would be, it's the dot product, right? The inner product is the dot product here. So I'm multiplying 3 and negative 4, that'd be negative 12, plus, then 2 times 6 is positive 12. This is 0, and that's the only pair I need to check, right? There's only one basis vector, so 1 times 1. There's only one pair I need to check. And the inner product of these basis vectors turned out to be 0. So the answer is, yes, W1 is orthogonal to W2, and vice versa, right? You can say W2 is orthogonal to W1. But the answer is yes. These subspaces of R2 are orthogonal. If I take any vector from one and any vector from the other one, they will have an inner product of 0. Alright, but that doesn't mean that they're orthogonal complements. Alright, that doesn't mean they're orthogonal complements, because as I mentioned before, if they are orthogonal, they're both subspaces of R2. Remember, I want to show this. If they truly are orthogonal complements, then R2 should be equal to, should be a direct sum of W1 and W2. All right. So that's my next question that I would need to answer. Is R2 a direct sum of W1 and W2? Alright, now this really comes down to, I can break this question up into two sub-questions, two smaller questions. So the first one would be is R2 equal to the sum of W1 and W2? And then the second question would be, is the intersection of W1 and W2 equal to the zero vector? Which we know is true because they are orthogonal subspaces. Right? So really the only one I need to answer here is R2 the sum of W1 and W2? Alright, so what would be the sum of W1 and W2? Now remember from, again, a previous video, the sum of two subspaces is the collection of all possible sums of vectors from W1 with vectors from W2. Alright, well, if W1 is made up of all the scalar multiples of 3, 2, so I take a scalar multiple, any scalar multiple of 3, 2, and then add it to a vector from W2, any vector from W2, which is just a scalar multiple of negative 4, 6. So you see W1 plus W2 would be made up of all the linear combinations of the vectors 3, 2, and negative 4, 6. So it would be the span of the vector of the set with the vectors 3, 2, and negative 4, 6. Right, and these are independent vectors here, right? If these were dependent, I could just shrink this to one vector, the span of a single vector, but these are independent vectors, right? There's only two of them, and they're not scalar multiples. So you see a basis for W1 plus W2, a basis has two vectors. Well, remember, R2 had dimension 2. So any basis of R2 is going to be a set of two independent vectors, which I have here. So this is all of R2. So the answer to that question is yes. Right, is yes. And then the second question is already answered because of the first question. When I said W1 and W2 are orthogonal subspaces, then their intersection must be only the zero vector, right? That was addressed in, again, a previous video on orthogonal subspaces. So, is the intersection of W1 with W2 equal to only the zero vector, right? Do they only share the zero vector? And again, yes. And the reason for that is because we have shown that since W1 was W2 were orthogonal subspaces, right, and orthogonal subspaces will have an intersection that's only the zero vector. So the answer to both questions here is yes. So the answer to my big question here is yes. R2, right, the vector space in question, is a direct sum of W1 and W2. All right. And putting this all together, since since W1 and W2 are orthogonal, and R2, all of R2, that whole vector space, is a direct sum of W1 and W2, then W1 and W2 are going to be orthogonal complements. These are orthogonal complements. All right. So we could say this. We could say that W1 is the orthogonal complement of W2, or W2 is the orthogonal complement of W1. I mean, either one of these means this, they're the same, right? They're both the same same meaning. Right. Okay. So again, notice I have the word "and" here. Both of these have to be true, right, in order for two subspaces to be orthogonal complements. They have to be orthogonal subspaces, right? So if you take any vector from one and any vector from the other, they'll be orthogonal. And they are, when you do a direct sum, right, the vector space that they're subspaces of is a direct sum of the two subspaces. Right? Both of these have to be happening in order for our subspaces to be considered orthogonal complements. Okay. Now let's take a look at a picture of this, right? I said I brought these up from R2 because I wanted to show you some pictures. So I got the GeoGebra.org website up, GeoGebra.org calculator, 2D calculator. So one of those, W1 was the span of the vector 3, 2, right? There's the vector 3, 2. And here's the span of 3, 2, right? There's W1 right there. Right? All the scalar multiples of W1 of the vector 3, 2. And then W2 was the span of the vector negative 4, 6. And let me back this up. There it is. Negative 4, 6. And the span of negative 4, 6 would be this pink line here. All right, so that's W2. So W1 is the blue line, W2 is the pink line, and you could probably tell from here if I zoom in, right? Remember, the inner product is the dot product. So when I say orthogonal, I mean perpendicular, the standard sense that they meet at a 90-degree angle. And it looks very much to me like these two lines, right, or these two basis vectors, v1 and v2, 3, 2, and negative 4, 6, looks like they meet at a 90-degree angle. They are orthogonal. And these subspaces, right, the blue line and the pink line, they look orthogonal as well. And can you see also that they would span vector 3, 2 and vector negative 4, 6 form a basis for R2 as well, right? So every vector in R2 can be written uniquely as a multiple of 3, 2 plus a multiple of negative 4, 6, right? A linear combination of 3, 2 and negative 4, 6. Thus that idea that all of R2 is a direct sum of these two subspaces. Okay. Great. And again, maybe I'm hoping you can see that in this picture. All right. So now another example. So that was from R2. Here's another one from R2. So W1 is the span of the vector 1, 4. All right, so again, another line through the origin in R2. W2 is the span of 5, 2. Again, another line through the origin. These are subspaces of R2, and again, the inner product here is the dot product. Right? So when I say orthogonal, I mean like the standard the standard usage of the word perpendicular. Right? So this time I'm going to take a look at a picture. All right, so let's get rid of these from the first example. So one of them is 1, 4. There's the vector 1, 4, and then here's the span of 1, 4. All right, that blue line that just popped up. That's W1. And then W2 is the span of the vector 5, 2. Here's the vector 5, 2. And here's the line with that, in the same direction as that vector, all the multiples of that vector. There's the pink line is W2, the span of the vector 5, 2. Now, hopefully it's clear to you that these are not orthogonal under the dot product. Right? These are definitely not crossing or intersecting at a 90-degree angle. All right, now there's still the vectors 1, 4, and 5, 2. They still form a basis for R2. All right, they're two independent vectors, 1, 4, and 5, 2. So you're going to see in this example that R2 is a direct sum of W1 and W2, but W1 and W2 are not orthogonal subspaces. So they can't be orthogonal complements, right? So just because we have a direct sum, doesn't mean that they're orthogonal complements. Right? So just be careful. So yeah, the first question again, is just if I'm asking, are these two subspaces of R2 orthogonal complements under the dot product? The first question I'll ask myself is, are W1 and W2 orthogonal subspaces? Alright. So again, there's only one basis vector for each again, so the only inner product I would need to check is the inner product with a basis vector from W1, which is just the vector 1, 4, with the only basis vector I'm seeing from W2, the vector 5, 2. And the inner product is the dot product, right? This is just 5 plus 8, right? 1 times 5 plus 4 times 2. That's 13, which is not 0. So you're definitely seeing that these two subspaces are not orthogonal subspaces. Right? So W1 is not orthogonal, a little slash to the orthogonal symbol, to W2. Right? So right away, I don't have to answer the other questions. I'm still going to, but remember, once one of these conditions isn't met, then it's no good, right? Once one of these conditions isn't met, right, where the vector, these two here, right, coming back, these both have to be true. The vectors have, the subspaces have to be orthogonal subspaces, and the inner product space itself, the whole thing, is the direct sum of those two spaces. If one of those doesn't hold, which I'm seeing that here, then we can immediately say, all right, then that means that W1 and W2 are not, right, orthogonal complements. Okay. All right. Now the second part would be true. Like I said, the R2 would be a direct sum of these two spaces, right? The vector 1, 4, and 5, 2 do form a basis for R2. So every vector in R2 can be written uniquely as a sum of a vector from W1 and W2. Pardon me. Right? So again, I'm not done. I'm just asking the question: is R2 equal to W1? Is it the direct sum of W1 with W2? So first question: is R2 equal to the sum? Right, just the plain sum. Well, what is W1 plus W2 here? All right, that would be the span. It would be the collection of all linear combinations of 1, 4, and 5, 2. Right? And I can't shrink this down any further because again, these are independent vectors. And a basis for this set is a set of two independent vectors. So this is R2, right? And these are sets with two vectors with two components. So this is R2. And what's their intersection? Well, you can see that back on my graph. You can see that back on the website, right? Their intersection is, the only thing that they have in common is the zero vector, right? Is the origin, these two subspaces. So yeah, be careful, right? Just because they're not orthogonal doesn't mean the intersection's not the zero vector, right? Here the intersection is just the zero vector even though they're not orthogonal. That can still happen, right? So the answer to this question is yes. The R2 is a direct sum of these two subspaces. All right, that's cool, but they weren't orthogonal subspaces to begin with, right? So like I said, I would, as soon as you figure out that one of them isn't true, one of the conditions, you can stop. Right? These are not orthogonal complements. I'm just showing you that, just because you have a direct sum, right? Just because the vector space is a direct sum of the two spaces doesn't mean that they're orthogonal complements. All right, because they have to be orthogonal subspaces as well. Right, both conditions have to hold. So if one holds and the other one doesn't, it's still no good. All right. Let me circle this. They're not orthogonal complements. All right. So next example, I'm going to get into R3. Right. So 3 dimensions, and again, I'll show you some pictures on the geogebra.org. They have a 3D calculator as well, as you've probably seen in other videos of mine. So this one, W1 is the span of just a single vector, 1, 1, 1. W2 is the span of another, just a single vector, 1, 2, negative 3. So this is a line in R3 containing the origin. This is another line in R3 containing the origin. Remember, the span of a single vector is a line. And these are both subspaces of R3, and again, the inner product will be the dot product here. All right, so let me show you a picture. All right, let me show you a picture. There's the 3D calculator. All right, so my first vector was 1, 1, 1. Right. So remember, so this goes red axis, green axis, blue axis. The components come in that order: red, green, blue. So this is 1 in the red, 1 in the green, 1 in the blue. This red vector that just popped up is the vector 1, 1, 1. And W1 was the span of 1, 1, 1. So this line here, this blue line that just popped up right now, I'll move this around, you can see the line, right, containing that vector 1, 1, 1. Okay. The other vector was 1, 2, negative 3. That's this green vector pointing down this way. Now it looks like, just if you look at the red vector and the green vector, let me get it to a view that might make it look a little easier to see here. Take this back to the home. All right. So maybe if you look at it like that, maybe it looks to me like, hey, these do look like they form a 90-degree angle, these two vectors. And then, if I pop in, here's this line containing that vector, that's W2, the span of the vector 1, 2, negative 3. And, it looks like to me, maybe you could zoom in or whatever, but it does look like to me that these do cross at a 90-degree angle, and being that the inner product is the dot product, I'm going to say that these are orthogonal subspaces. All right, but are they orthogonal complements though? All right, they're orthogonal subspaces, sure, but when you put them together, take their sum, do you get all of R3? And the answer is no. Right? I mean, the vectors 1, 1, 1 and 1, 2, negative 3, they point in two different directions, right? Two independent directions, sure. But remember, the dimension of R3 is 3. I need a third direction. I need a third independent vector to give me a basis for R3 to be able to create any vector I want from R3. I can't do that with these two. Right? These don't span R3. In fact, they only make this plane. Right? Here's the plane with those with those two lines on it. right? This would be the sum of W1 and W2. The sum of W1 and W2 would just be this plane, not all of R3. All right, so the first condition's met, it looks like, W1 and W2 are orthogonal subspaces, but R3 is not a direct sum of W1 and W2, and I'll show that on paper. All right. So again, the question is, are W1 and W2 orthogonal complements? Right. So first question, are W1 and W2 orthogonal subspaces? Of R3. Okay. So again, just like the last two examples, I only need to check one pair, right? This has one basis vector, this has one basis vector. So I'm only doing the inner product of 1, 1, 1 with 1, 2, negative 3. All right, and that would be 0. So yes, right, because that'd be 1 plus 2 minus 3. Right. So yes, W1 and W2 are orthogonal subspaces. All right. If you take any vector from W1 and any vector from W2 and take their inner product, you will get 0. But in order to be orthogonal complements, they need to make up the entirety of R3, and they don't. I showed you that in the picture. Right. Is R3 a direct sum of W1 and W2? Because remember what it means to be orthogonal complement. Remember, the orthogonal complement of a set of a subspace of a vector space is all the vectors in this vector space that are orthogonal to every vector in W1, say. Right. So W1 has dimension 1, right, has a basis of one vector. So that means I'm missing two directions, right? Remember, R3 has dimension 3. I'm missing two directions. So the orthogonal complement would have to have dimension 2. Right? And you see W2 here has dimension 1. And that's something I'll point out as well. I'll write a little note here as when we get to the bottom. So is R3 a direct sum of W1 and W2? No. W1 plus W2 would just be the span of two vectors, right? The span, and these are independent vectors, so I can't shrink the list. Right? The span of 1, 1, 1 and 1, 2, negative 3, right? The set W1 plus W2 would be the linear combination of all linear combinations of the vectors 1, 1, 1 and 1, 2, negative 3, and this is not equal to R3. Remember, because R3 has dimension 3, this is only dimension 2, as you saw in the picture. Right, there, that shaded blue, that plane there, that's W1 plus W2. But you notice it is not all of R3. There are vectors in R3 that I cannot write as a linear combination of 1, 1, 1 and 1, 2, negative 3. Right. So no. Right, the answer to this question is no. Now the intersection is still just a 0 vector, right? You saw that. If I took W1 intersected with W2, that's just the 0 vector, but that doesn't matter. Their sum is not all of R3. So again, if one of these conditions isn't met, right, one of them is they're orthogonal subspaces, sure. Any vector from W1 and any vector from W2 are going to be orthogonal, but there are some vectors from R3 that can't be written as a sum of vectors from these spaces. So because of this, W1 and W2 are not orthogonal complements. Now, if I rewrote the problem, if I changed it up a bit, instead of V being all of R3, if I said my vector space was just the span of these two vectors, right? If this set was here instead, then these would be orthogonal complements. But they'd be orthogonal complements in this vector space. They are not orthogonal complements in R3. I hope that makes sense. All right. Because this space is the direct sum of W1 and W2 and their orthogonal subspaces. Right? But they don't make up all of R3. So let me say that one more time. These two spaces would be orthogonal complements if this was the vector space I was looking at. But they're not orthogonal complements in R3. Right? As I mentioned, one thing I need to point out. Remember, V equals, right, remember the vector space we're looking at is a direct sum of a subspace and its orthogonal complement. All right, so another result from that I probably should have written out earlier is that the dimension of the vector space will then be equal to the dimension of the subspace W plus the dimension of the complement, the orthogonal complement of W. All right, so this is a way to check too. Right? So like, look at these two here. All right, this has dimension 1. This W1 has dimension 1. W2 has dimension 1 as well. This has dimension 3. 1 plus 1 is not 3. So there's no way this could happen. There's no way that these could be orthogonal complements. Right? If you have orthogonal complements, the sum of their dimensions will be the dimension of the larger vector space that they are subspaces of. But again, if I change V here to this set, because these are subspaces of this space, then it would work. 1 plus 1 equals 2. But the vector space in question here was R3. So you got to really, again, pay attention. I say pay attention a lot, right? Because you have to. All right. Next example. So again, still in R3. Right, still in R3. This time I have a plane and a line instead of two lines. So W1 is the span of a set with two vectors. So this has dimension 2. And W2 is the span of a single vector, right? This will be a line through the origin. This has dimension 1. And the vector space is R3, dimension 3. 2 plus 1 is 3. That means these might be orthogonal complements, right? Doesn't mean they will be. All right, but 2 plus 1 is 3. They might be. Now, if the sum of these dimensions weren't 3, I'd know that they weren't orthogonal complements. It'd be that easy. But the sum of the dimensions is 3, the same as the sum of the dimension of the vector space, so they might be orthogonal complements. All right, but I still have to check. All right, so same questions. I'm going to ask myself the same set of questions. First question. Are W1 and W2 orthogonal subspaces of R3? All right, so this time I have a little more to check than just one pair of vectors. Because this time the first space here, W1, has two independent basis vectors. So I have two choices there for the first slot in my inner product, and then the W2 has this one basis vector. So 2 times 1, that's two different inner products I need to take. So one of them is the inner product of 1, 0, 1 with negative 1, 1, 1. And again, a basis vector from W1 with a basis vector from W2, and I look at all possible pairings. This would be 0, right? This would be negative 1 plus 0 plus 1. The inner product is, again, the dot product. So this is 0. but I also need to check the inner product of, that was 1, 0, 1 with negative 1, 1, 1. Now how about 1, 1, 0 with negative 1, 1, 1? Again, it's a basis vector from W1 with a basis vector from W2. And again, it's the dot product, negative 1 plus 1 plus 0, that would be 0 again. And that's all possible pairings. Right? That's all possible pairings of basis vectors from W1 with basis vectors from W2. So putting these all together, we're seeing that W1 is orthogonal to W2. So the answer is yes to this question. Right? That does not mean that they are orthogonal complements. Now, if you think about it, look at these basis vectors, 1, 0, 1, 1, 1, 0, negative 1, 1, 1. Wouldn't these three form a basis for R3? You can think about that, and you can verify that for yourself. So I'm gonna guess, and it would be true, that R3 is a direct sum of W1 and W2. So R3 is a direct sum of W1 and W2. I'll just say yes. All right. Because again, W1 plus W2, I'll write it out. W1 plus W2 would be, any vector from W1 plus any vector from W2. That's any linear combination of 1, 0, 1 and 1, 1, 0 plus a scalar multiple of negative 1, 1, 1. That's any linear combination of these three vectors. That would be the span of these three vectors, 1, 0, 1, 1, 1, 0, and negative 1, 1, 1. And you can verify easily that these are three independent vectors. So I have a basis that's a set of three independent vectors. So this has dimension 3, and R3 has dimension 3. This is R3. This is R3. These are all vectors with 3 components as well. This is R3. All right. So and we know from here, right? We know from here, because W1 and W2 are orthogonal, their intersection must be just a 0 vector. So like I said, the answer is yes to, is R3 a direct sum of W1 and W2? If I were to take a vector from R3, I should be able to write it as a unique, in a unique way, one and only one way, as a vector from W1 plus a vector from W2. So all this together, yes, these two subspaces are orthogonal complements in R3, right? So yes, W1 and W2 are orthogonal complements. Yeah, again, we could say that W1 is the orthogonal complement of W2. Say that, or you could say that W2 is the orthogonal complement of W1. They mean the same thing. All right. They would mean the same thing. And we have, they're orthogonal subspaces, and R3 is a direct sum of W1 and W2. Let's take a look at some pictures. All right. Again, I'm in R3 here. I can show you some pictures. So the first one's a plane, W1. All right, let's go back to the GeoGebra site. Clear all this stuff from the first example. Back to the home view here. All right, so remember it was 1, 0, 1, and 1, 1, 0. Those two vectors there, and then the span of those, right? The span of those two vectors would be this plane, right, which I have here. Right, there's the plane spanned by 1, 1, 0, 1, 0, 1, and 1, 1, 0. All right. Now let's take a look at the third vector, the vector that is the basis for W2, negative 1, 1, 1. And maybe you can see, if I tilt the plane like this, maybe you can see that it looks like they form a 90-degree angle, right? That plane and that blue vector. and here's the span of negative 1, 1, 1, that line. This plane and that line do form a 90-degree angle, right? And the dot product is the inner product here. So orthogonal means perpendicular. Yeah, looks like they are orthogonal subspaces, right? And they would span, right, R3, these three vectors, because you're getting two different directions with the red and green vector, and then you're getting a third different direction with the blue vector. And any set of three vectors that go in three different directions will make up all of R3, will span R3, be a basis for R3. So you could say that R3 is a direct sum of W1 and W2 here, right? That plane and that line. And you should be able to take any vector from R3 and write it, express it as a vector from the plane plus a vector from the line. And do that in a unique way. Right? Like I said, though, I'll show you in the next video how we're going to do that. Okay, wonderful. Alright, so far, all these examples, I've been asking to verify whether or not, determine whether or not two subspaces of a vector space, an inner product space, determine whether or not two subspaces are orthogonal complements. On my last couple, I have two more examples. Right, the last couple examples are finding orthogonal complements to a given subspace. Alright, so suppose we're given that W is a subspace of inner product space V. Find the orthogonal complement of W, which would be, W with the orthogonal symbol above it. Right? And this is where I'm going to bring back the definition of orthogonal complement here. So my subspace W, and now I'm back to R2, okay, under the dot product for my inner product space. W equals the span of the set with the vector 3, 5. Right. Remember, this is just the span of a single vector. It's a line, and let's take a look at a picture. All right. So we're back in R2, and let's clear this stuff, and I'll just put in the vector 3, 5. Right. All right, there's the vector 3, 5. Let me zoom out a bit, and put in W space W here, the line going through the origin in the direction with all scalar multiples of that vector. All right, and maybe I'll change their colors a bit. Right. So we got green there, and let's change this color to red. Okay, so you see there's the vector 3, 5, and then here's the span of 3, 5, right? Just all the scalar multiples of 3, 5, forming a line through the origin. We're asked to find the orthogonal complement. So remember, this is R2. It's 2 dimensions. So I've got 1 dimension now, right? I've got 1 direction, 3, 5. I'm just looking for another direction, right? I just need 2. That's orthogonal to this, and then the span of that will be the orthogonal complement. Right? Well, on paper, what we're looking for is the following, right? Remember, if W is the span of 3, 5, remember then W complement, right? The orthogonal complement of W is every vector. Remember the little definition from one of the earlier pages, right? The first page of this video is every vector from R3, right? Remember our vector space here, R2. Yeah. Our vector space here is R2. It's every vector from R2 such that the inner product of those vectors with any vector from W is equal to 0, right? And this is for all vectors in W. Right. So we're trying to find every vector in R2 that's orthogonal to every vector in W. Right. So let me write that out. Right, we're going to try to find every vector v equals, and again, what does this mean? What does every vector in R2 look like? You know, it has two components, say v1, v2, or x1, x2, whatever you want. Something with two components, a, b, x, y, belonging to R2, such that the inner product of v with w equals 0 for any vector for any w in w. Now, what does w look like? All right, what does w look like? Well, if w is any vector in w here, remember w is a span of 3, 5. So remember that means it's a scalar multiple. I'll say c for some scalar c times the vector 3, 5. Right, this belongs to w, right? Where again c is just any scalar, right? C is any scalar. Okay. All right, so let's see what this looks like. What does this equation look like when I substitute my vectors in? All right, so we have, and taking this down, seeing what does this equation look like? That'd be the inner product of, you know, v1, v2 with, you know, some scalar multiple of 3 and 5. All right, well, do you see how the scalar multiple won't matter? Because remember the homogeneity property of inner products. So you're going to see that my scalar multiples won't matter. I could pull the scalar out, and really all we're doing is taking the inner product of some vector from R2. Right, here was our general vector from R2 with the basis vector of W, or the basis vectors of W, and there's only one of those, and that's the vector 3, 5. Right, and when is this equal to 0? Right, and again, this is for any scalar. Now I know if the scalar were 0, that would be easy, but this needs to work for any scalar. The only way this is going to work for any scalar is if this is 0, right? Is if this inner product is 0. So what does that look like? I need this to be 0. Well, that's 3v1 plus 5v2 equals 0. I need this solution. I need this equation to be satisfied. I need this equation to be satisfied. All right, well, you know how to solve equations. All right, now there's one equation with two variables. All right, so one of these is a free variable. All right. Now, if you'd like, I mean, this would be silly because it's such a small system. There's only one equation. You could make an augmented matrix for it where, you know, here down the first column, the coefficients of v1, down the second column, the coefficients of v2, then a little equal sign, and 0 over here. And I could put this into, you know, reduced echelon form or reduced row echelon form by simply multiplying everything by 1/3 to get that leading one, that leading one in the first row, the only row. And I have 5/3 and then, you know, 0. And then we see from this, you know, there's a pivot, right? The leading one is. So my free variable is v2. I'm going to let v2. I'm going to replace it. You know me. I like to replace my free variables with other parameters, other expressions that represent real numbers. And because of this fraction here, I'm going to replace v2 with 3t, right, where t is just some real number. And if v2 equals 3t, then this equation tells me that v1 plus 5t, right, 5/3 times 3t, 5t, equals 0. So v1 must be equal to negative 5t, right, subtracting 5t from both sides. So then our solutions to this equation here, the vectors, right, the vectors that are orthogonal, all orthogonal to some multiple of 3, 5, look like this. Right. Then our vectors v1, v2 are just, they both have t in it. Right? I'll pull the t out. Just some multiple of the vector negative 5, 3, right? Negative 5 for that first component, 3 for the second component. So our solutions to this equation is just any scalar multiple of the vector negative 5, 3, or the span of the vector negative 5, 3. And there's our orthogonal complement, right? So therefore, the orthogonal complement of W is the span of the set with the vector negative 5, 3. And you can double check this, right? Let's check this. W was the span of 3, 5, and my orthogonal complement is a span of negative 5, 3. If you did the dot product with 3, 5 and negative 5, 3, you'd get negative 15 plus 15, or 0. So these are orthogonal subspaces, and 3, 5 and negative 5, 3, those two vectors together form a basis for R2. So R2 would be a direct sum of the span of 3, 5 and the span of negative 5, 3. And looking back, look at a picture. All right, so that was 3, 5, and then put in another vector here. This vector is negative 5, 3, and you can see the orthogonality. Right? You can see them meeting at a 90-degree angle, and again, the span of this vector would just be the line containing it. Right? There it is, right there. Right? And they definitely form these two vectors, 3, 5, and negative 5, 3. Right? They form a basis for R2. So these subspaces, the span of 3, 5, the span of negative 5, 3, their direct sum would make up all of R2. Right? Any vector in R2 should be able to be expressed uniquely as a multiple of 3, 5 plus a multiple of negative 5, 3. Right? A vector from W1, a vector from W plus a vector from the orthogonal complement of W. Right? I'll write that here. Right? And we would have R2 is W plus with the circle around it, the direct sum of W with its orthogonal complement. Right? And this should always be the case. Any vector space should be a subspace, the direct sum of a subspace plus its orthogonal complement. This should always happen for any subspace and its orthogonal complement. Alright, so I'm going to do one more like this where I'm asked to find, and did you notice how it ended up boiling down to solving a system of equations? So that one just had one equation though. But finding these orthogonal complements boils down to solving a system, which you've done many, many times, I'm sure, before now. Alright, so this time I'm in R3. Alright, again, under the dot product one more time. Alright, the inner product's the dot product. So W is the span of 1, 0, 3. And that's a subspace of R3. Right? Now this is just, again, a line going through the origin. Let me show you a picture. So go back to the 3D calculator. Let's get rid of the last examples stuff. Back to the home view. Alright, so the vector this time, the basis vector is 1, 0, 3. Alright, so there's 1, 0, 3. And here's the span of that vector. Just a line going through the origin in the direction of that vector. There's the span of 1, 0, 3, just a line. Now that's just one direction. Right? That has a dimension 1. So the orthogonal complement in R3, right? We're in R3. The orthogonal complement needs to have a dimension of 2. So the orthogonal complement has to be the span of 2 vectors, or a plane. And we're going to see that happen when we go and solve some system. Right? So what are we looking for? Right, we're trying to find all the vectors from R3. All vectors, say v equals, v1, v2, v3. Right? These are vectors from R3, so they have 3 components this time. Or you could do a, b, c, x, y, z, whatever you want. Right? Find all the vectors from R3 such that the inner product of those vectors with any vector from W, right, from the span of 1, 0, 3, equals 0. Right, where W is any vector from set W here, which will be just some multiple, again, some scalar multiple of the vector 1, 0, 3. Right. Where C is a scalar, but this belongs to W, and again, C is any scalar. So like I said before, the scalars won't really matter because of homogeneity, the homogeneity properties of the inner product. So when I'm checking this out, when is the, I'm finding all these vectors from R3 whose inner product with vectors from W is equal to 0. Well, if you're orthogonal to vectors in W, that means you're orthogonal to the basis vectors. So the only ones that are going to really matter are the basis vectors of W. Now this one has only 1. If there were 2, I'd be setting up 2 equations. Right? If there were 3, I'd be setting up 3 equations and solving a system. All right, but again, this is just one with one basis vector, so I'm only going to be setting up 1 equation and solving that equation. But just know that if your set W has 2 basis vectors, you'll be getting a system of 2 equations. 3 basis vectors, you'll be getting a system of 3 equations, etc. All right, so what we're looking at here is the inner product of just any vector from R3, v1, v2, v3, with our basis vectors from W. Well, there's only one of them, just 1, 0, 3. And when is this equal to 0? And this is the same thing as this equation, right? Remember this is the dot product, right? The inner product's the dot product again. So this is just when is v1 plus 3v3, when is that equal to 0? Right, when is that equal to 0? So I've got one equation with 3 variables. Now technically there's 0 v2 here. Right? So there's one equation with 3 variables, meaning there's going to be 2 free variables. Right. And I'll set up I'll write the augmented matrix again. Really, again, kind of silly, but there's 1v1, 0 v2, 3 v3, equals 0. And this is already in reduced row echelon. Pardon me, reduced row echelon form, right? It's got a leading 1. So I look at my pivot. There are 2 free variables, so I'm going to let v2, I'm going to call that s, right, for any real number s, and v3, I'm going to call that t, right, where s and t are real numbers. So from that only equation, this only row here, I'm seeing that v1 would have to be negative 3t. Right, we'd have v1 plus 3t equals 0, 3v3 equals 0. So our solutions look like this. So all the vectors that are orthogonal to all the vectors in W look like the following. Right, so my v1, v2, v3 here are, now I can do v1 is negative 3t, v2 is s, and v3 is t. There are 2 free variables, so I can split this up as a sum, one of vectors involving s and one involving t. So this would be s times the vector 0, 1, 0 plus t times the vector negative 3, 0, 1. So what we're looking at here is any linear combination of the vectors 0, 1, 0 and negative 3, 0, 1 would be orthogonal to any vector from W. Right. So W, So the orthogonal complement of W is the span of the set with vectors 0, 1, 0 and negative 3, 0, 1. As I said it should have been, right? I said it should have a span of two. It should be a span of two vectors, right? Because this had dimension 1. We're finding the orthogonal complement in R3, so the sum of the dimensions of orthogonal complements should be the dimension of the vector space. Right. So 1 plus 2 equals 3. Looks like it's working out. Okay. And another thing you should be noticing too is that R3 must be W plus W complement, right? W, the direct sum of W plus W complement of W and W complement, the orthogonal complement of W. All right. And again, this should always happen for any subspace. If you want to double check, are these orthogonal? Take the dot product of 1, 0, 3 with 0, 1, 0, that would be 0. Take the dot product of 1, 0, 3 with negative 3, 0, 1, that would also be 0. Right? These are orthogonal subspaces of R3, and these three vectors, these three basis vectors, form a basis for R3. Right? R3 is a direct sum of W and the orthogonal complement of W. Right. All right, and just be careful, right? Like I said, there are, if the space you're given, and you're asked to find the orthogonal complement of it, if the space you're given has two basis vectors, you're going to be setting up a system of two equations. If it has three basis vectors, you're going to be setting up a system of three equations, and so on. Right? So far, my only two examples here, I had a system with one equation, but just know that there can be more. All right. So hopefully the concept of orthogonal complement was clear, right? The orthogonal complement of a subspace. And I hope you enjoy practicing problems like I've shown here, where you're given two subspaces of an inner product space and asked to determine if they're orthogonal complements, or if you're just given a subspace of an inner product space and asked to find the orthogonal complement. You should be able to do both those things, right? So hopefully in practicing those you'll get better. It's the only way to do that, right? And thank you very much for watching.